collisions. It is the time of rest. It is the time in which the electron is not undergoing any of the collisions. So it is the relation between resistivity and relaxation current that help us understand the increase in current. And today we will study about internal resistance of a cell. Cell basically constitutes of two things which you already know. That is the electrodes. We have electrodes which are positive electrodes and negative electrodes. Then we have the electrolyte component of cell. The electrolyte of a cell. Now this electrolyte, it itself contains the positive ions, it contains the negative ions. The negative ions, they move from high potential to low potential, and they contain, of course the electrolyte contains neutral atoms. So this is the basic understanding of a cell. It contains electrodes which are positive and negative, it contains electrolyte, and the electrolyte itself has what you can say huge number of positive, negative ions and neutral atoms. Now let us consider, you know that the positive ions, they are moving from low potential to high potential, and the negative ions, they move from high potential to low potential. This is something which we all know about cells. Now when these negative ions, they are moving inside the electrolyte, there the electrolyte offers some resistance. It is electrolytic resistance to the negative ions. Actually these negative ions are swimming against the background of positive ions and neutral atoms, and when they are trying to swim against the background of positive ions and neutral atoms, they experience a kind of resistance, and that resistance is called electrolytic resistance to the negative ion. You can say it is, if you want to define internal resistance of a cell, it is the resistance offered by, it is basically the resistance offered by electrolyte of a cell. It is the resistance offered by the electrolyte of a cell. To whom? To the negative ions. Because these are the negative ions which are moving from high potential to low potential, and they try to constitute current, and that is the resistance offered by the electrolyte of a cell to the negative ions. And where are they moving? Negative ions moving between the electrodes. They are moving between the electrodes. So we need not mark the statement, but we can understand it is nothing but the resistance offered by the electrolyte of a cell to whom? To the negative ions moving between the two electrodes. Now let us try to establish the relationship between, we are trying to establish the relationship between EMF of a cell, the internal resistance which is denoted, internal resistance is denoted by a letter small r, then external resistance capital R, current I. How are these terms correlated in a cell? So let us take the example of a simple cell. We can take the example of a simple cell where we can have an external resistance connected to a cell, and the cell itself is having, this is external resistance R, internal resistance E, EMF of the cell, and this is the circuit. Let us say I is the current flowing in the circuit. I will define 2 points. I will call this as X and this as Y. Now total EMF, this total EMF is the work done. Basically it is the work done. Can we write it here? We will write it here. You can use this part. The EMF is total work done. It is the total work done to move unit charge. It is the total work done required to move unit charge through the circuit. through the circuit, or sometimes we may call it along the circuit. It is the total work done to move unit charge. It is the work done to move unit charge through the circuit. Now this E can be written as the sum of V plus V dash. What is V? It is the work done to move unit charge. It is the work done to move unit charge from this X to Y through the external resistance. We can say it is the work done to move the unit charge from X to Y through external resistance or against external resistance. And what is this V dash? V dash is work done to move unit charge from, one is V dash, that is the work done in traveling, making the charge travel like this. It is moving from X to Y through the external circuit, that is external resistance R. And the second part, V dash, is the work done in making the charge travel through this small r, internal resistance, and coming back to the negative pole. So work done to move the unit charge from Y to X through the small r, that is internal resistance. Here it is external resistance. It is from X to Y, it is from Y to X. So overall, I can write this as, like this. I can write this as E is equal to V plus V dash. What is V? Work done in carrying the charge through capital R, that is external resistance, and small v dash is the work done in carrying the charge through the small resistance, internal resistance. This can be written as, according to Ohm's law, it is capital IR plus the current is same. It is the work done in carrying the charge through internal resistance of the cell or through the cell. So we can use this particular expression and we can write it like this, and current I is E by R plus R. This is simply dimensionally similar to what we have in Ohm's law. Current I is equal to EMF divided by total resistance. Now you can see this capital R and small r, they are in series. Capital R and small r, they are carrying the same current. How do you understand that two resistors are in series? If they carry same current. If current through them is same, that indicates that they are in series. They may not appear to be in series, but still they will be in series if they have same current. So capital R and small r, they are in series. So the total resistance will be R plus R. We find the total resistance in series by adding the resistances. So capital R plus small r, total resistance, EMF upon total resistance is giving you current. Now little further, if suppose I have to correlate it with EMF, so I can get V is equal to, from this, E minus V dash. V is equal to E minus IR. So I can get it like this, E minus V upon I is equal to small r, the expression for internal resistance. How can I, little manipulation here, or we can say arrangement of the terms. E minus V upon I can be written as V by R. So this is the expression for internal resistance in terms of EMF, internal resistance, capital R, I and V. How are they all correlated? This is written like this also, E by V minus 1 into R is equal to small r. The one and the same expression. A very, very important expression. And from this expression we derive a very important conclusion that if we plot a VI graph for a cell, not for Ohm's law, remember, not for a circuit, but for a cell. If for a cell we plot it, the graph will be like this. What is it indicating? This is indicating a slope minus r, because y is equal to mx plus c is the equation of a straight line, and here you are getting v is equal to minus ir plus e. So e is a constant independent of r, and the slope is V and I graph आप बना रहे हैं, Y and X is V and I, so the slope is minus R. This is for a cell. This is for a cell. Okay, so we have established the relation, and we can see what happens when the cells are connected in series. That we'll see in the next episode. Thank you.